Today. So today we will be going over our gas laws, and we're going to be continuing this onto part 2 of our gas law notes. So for today, you do need to make sure that you've got your notes, something to write with. You need a calculator, and then possibly you'll need a periodic table. So make sure you've got all 4 of those things, and we're going to go ahead and get started on this. Okay, so last class we ended the class when we talked about the ideal gas law. So we talked about PV equals nRT. Now for today, we're actually going to talk about some deviations from the ideal gas law. And this is specifically looking at molecular weight and density. So we do actually have a formula basically based off of our PV equals nRT for solving for something like density or molecular weight. And so what do we do for that? Well, we know that our PV equals nRT. That N is the number of moles. And so when we're talking about moles, a lot of times we know that we can actually solve for our molar mass using our number of moles. And so essentially what this formula is going to do is actually skip a step for you to prevent you from having to solve for moles, and then after you solve for moles, convert into density. Now, for this, we actually use P equals mRT over V times the molecular weight, because we know that with our number of moles, we know that to solve for that, we're going to take our mass divided by our molecular weight, and that will tell us what our number of moles actually is. So it basically takes that formula and plugs it in. Another thing we know is that density equals our mass divided by our volume. So again, we can take that ideal gas law and we can rearrange that formula, and we can actually solve P equals dRT over MW, which is, again, the molecular weight. And so we can actually solve for our density using our PV equals nRT. Now, we can actually rearrange this all to get a single formula that we use, and we call this the molecular weight kitty cat. Why do we call this? It is the molecular weight kitty cat because, I'm actually move this over here, because the molecular weight kitty cat puts dirt over its P, right? So in the litter box, it's going to put its dirt over the P, all right? And that's just a way to help you remember your PV equals nRT, solving for that molecular weight and that density, all right? Okay, so let's actually go ahead and solve a problem that uses the molecular weight kitty cat. So an unknown gas with a mass of 205 grams occupies 20.0 liters at standard conditions. What is the molar mass of the gas? Okay, well, we know that the molar mass is your molecular weight. That equals dRT over P. Okay, so we got the molecular weight equals dRT over P. So what we're going to do is we're actually going to solve for our density first. We know that density equals mass over volume, right? So they told us we have 205 grams, and that occupies 20 liters. So density equals 205 grams divided by 20.0 liters. And that's what's going to give us our density, and we have everything else that we're going to need to actually solve for this equation. Now we plug this into our calculator, and we're going to get 10.3 grams per liter. That would be our density. Now let's go ahead and plug that into our formula. So molecular weight equals D, which is our density, 10.3 grams per liter, times R. Now for this one, we do need to figure out which R we want to use. Now remember, for your R, you're going to choose it based off of what version of pressure you have. Since they don't give us pressure, but they do give us that it is in standard condition, we can essentially choose what we want to do. So I'm going to actually scroll back up here, let y'all see those ideal gas constants again. I personally like to use atmospheres. I think it's easier, so that's the one that I'm going to use. So I have, 0.08206 liters times atmospheres over moles times Kelvin. Okay? And then we keep on going. So we still need to add our temperature and our pressure. We know that our temperature is standard temperature, which is 273 Kelvin, and our pressure is standard pressure, 1 atmosphere. Cancel out our atmospheres, cancel out our volume, cancel out our temperature. We're going to be left with grams per mole. Well, that, remember, is your unit for molecular weight. So I'm going to take this, I'm going to multiply all of this out, and what I'll find is I have 231 grams per mole. And then that would be my answer. All right. So that would be for solving or a deviation from the ideal gas law. So using it to actually solve for something like molecular weight or density. So moving on past that, the next thing we're going to talk about is Dalton's law of partial pressures. And this is something that we've talked about a little bit briefly in the past, but really not that much, because it is fairly straightforward in terms of what we're actually looking for. So it says for a mixture of gases, the total pressure exerted is the sum of all the pressures. Well, that makes sense, right? If I've got a bunch of pressures inside of a container, I can add them all up, and that's going to tell me what the total pressure is, right? And here would be our formula for that. So the total pressure, P tot, equals P1 plus P2 plus P3, and so on. Okay, so we don't really have to do a whole lot with that. Now, you can also use the pressure total equals nRT over V plus second nRT over V plus third nRT over V, and so on. Essentially, that's taking PV equals nRT, and you're using your number of moles that changes per substance. Okay? All right. For whatever gas it is, you can actually condense all of that into your pressure total equals the number of moles total times RT over V. Essentially, it's just an easy way to condense all of that down. Okay. So looking at this, we've got a practice problem here. It says a mixture of gases at 0 degrees Celsius and 3.4 atmospheres contains 0.025 moles of H2, 0.040 moles of O2, 0.065 moles of Cl2. Assuming ideal behavior, what is the partial pressure of each of these gases? Well, so there's a simple way that we can solve this. For our pressure of hydrogen, it's going to equal the total pressure, 3.4, times, essentially what we can do is we can actually take our number of moles, 0.025, divided by the total number of moles. So this is moles of hydrogen, and we're going to divide that by the total number of moles. Essentially, it's doing all the other work for us. And so if we're looking for the pressure of a gas, we can do our total pressure, so P tot, times the moles of the gas divided by the total moles. It's just another way of condensing this formula down. So we've got our pressure total times our number of moles divided by our total number of moles, which is 0.13 moles. We're going to solve that, and we're going to find that we have 0.65 atmospheres for hydrogen gas. Then we're going to do the same thing with our oxygen and with our chlorine gas. So 3.4 times 0.040 moles of oxygen divided by the total number of moles equals, and that's going to give us 1. And then we're also going to do that with chlorine. So 3.4 atmospheres times 0.065 moles of chlorine divided by our total number of moles equals, and this one's actually going to give us 1.7 atmospheres for chlorine. Okay, and then you can actually go back in and double check, and what should happen is these should add up to be pretty similar, pretty close to our total pressure. Okay, in this case it's 3.35, which is very, very close. All right. Now, another way you could be asked is the following picture represents five gases that make up air. Determine the total pressure of the air. And so essentially we know that based off of Dalton's law of partial pressures, your pressure total equals the sum of all of your other pressures. So the total pressure equals P1 plus P2 plus P3 and so on. So our pressure total equals 20.9 plus 78.1 plus 0.97 plus 1.28 plus 0.05. We're going to add all that up and we'll find that our total pressure equals 101.3 kPa. And then that would be our answer there. All right? So that would be solving for our pressures, the individual pressures that we have in a gas, or even the total pressure. Now, one thing that we do talk about with all of this is called the mole fraction. And the mole fraction is basically just your number of moles of a given component in a mixture compared to the total amount of moles in the mixture. So it's the part divided by the whole, just like we find with any of our fractions, right? Part divided by whole. Now, we do use this symbol right here. It's essentially an X. It's used to symbolize our mole fraction. And how do we actually solve for this? Well, it says, I'm going to actually put this on the next page here, but it says, if 30 grams of lithium chloride is dissolved in 100 grams of water, what is the mole fraction of lithium chloride? Well, we know that for our mole fraction, it's going to equal the number of moles of whatever we're looking for divided by the number of moles, the total. Okay, and so we need to figure out how many moles we have. So to do that, we need to do some mole conversions here. We need to convert from grams into moles. So I have 30.0 grams of lithium chloride. I'm going to convert from grams of lithium chloride into moles of lithium chloride using my molar mass. I have 1 mole for every 42.394. And I'm going to plug that into my calculator and I will find 0.708 moles of lithium chloride. Now I need to do the same thing with my H2O. So I found that I had 100.0 grams of H2O. I have grams of H2O on the bottom. I'm going into moles of H2O. For every 1 mole, I have 18.02 grams. I'm going to plug that into my calculator and I will find that I have 5.549 moles of H2O. So then if I am solving for the mole fraction of lithium chloride, so my mole fraction equals 0.708 moles of lithium chloride divided by the total number of moles. So for the total, I'm going to take those two numbers over here and I'm going to add those together and I'm going to find that that is going to equal 6.25 essentially. 6.257, I think. All right, and then I plug that number in right here. All right, and then I'm going to solve for that, and I will find that my answer is 0.113 is my mole fraction for lithium chloride. It's not Cl2, it's just a Cl. Okay. Hopefully that makes sense to y'all with our mole fractions there. Essentially, you're just solving for to figure out what portion of that compound in the mixture is that compound. Okay. Another thing that we have is that the partial pressure of a particular component of a gas is the mole fraction. So essentially, again, we're talking about mole fractions and we're talking about pressures. We can use those two things to actually solve for more information. So if I know the total pressure and I know the mole fraction, then I could solve for the partial pressure. Or if I know the total pressure and I know one of the partial pressures, then I can solve for my mole fraction. So here's a question. It says, in a mixture of two gases, the partial pressure of methane is 0.175 atmospheres, and the partial pressure of oxygen is 0.250 atmospheres. What is the mole fraction of methane in the mixture? Okay, so essentially what I know is that I've got P1 over P total, and that's going to give me my mole fraction, right? I basically rearranged this equation right here, and I'm solving for my mole fraction because that's what they want me to solve for. So to do that, what I need to do is I need to solve for methane in this mixture, specifically methane. So I know I have 0.175 moles, and that's going to be my partial, divided by the total pressure or total number of moles, which is 0.425 moles. So this is moles of methane. This is the total number of moles. And we're going to plug that into our calculator, and we will find that we have 0.412 for our CH4. And then that would be my mole fraction. Okay, now if they didn't tell me my partial pressures, I could flip that around, and they gave me the mole fraction. I could actually flip that around and actually solve for one of those partial pressures. So let's take a look at the next part. So again, we're kind of building on everything that we've learned with each of these steps, right? We started with doing a deviation of the ideal gas laws. Then after that, we moved over to Dalton's law of partial pressure. And then from there, we started talking about different ways that we can actually use Dalton's law of partial pressure to figure out something like a mole fraction. All right. Now, the last thing we're going to talk about is when we collect gases over water. Okay. Essentially, what we're doing is we're gathering those gases over the top of the water because the water exerts a lot of pressure upwards, which prevents it from actually being dissolved back into the water. All right. So how do we do this? Well, it's essentially Dalton's law of partial pressure, okay, where we can actually solve for the pressure of the individual gas by just subtracting out the pressure from the water from the total amount of pressure, okay? And that would be what we have right here with our formula. So it's the pressure of the water plus the pressure of the gas is going to give us our total pressure. So if I'm solving for the pressure of the gas, then I would just subtract that water pressure from the total pressure. Okay, so here is a question that we've got over collecting hydrogen over water. So it says 50 milliliters of hydrogen was collected over water, and it has a pressure of 850 torr at 27 degrees Celsius. What would be the volume of the dry gas at STP? Okay, so this is actually going to be somewhat tricky, right? It's really not, but in terms of it's not a one-step problem. So what would be the volume of the dry gas? Well, this right here has to be the first thing that we're going to do here, right? We need to actually subtract out the water pressure from our total pressure first, okay? So let's do that. We know that the pressure of gas A plus the pressure of the water should equal the total pressure that we have. If we're solving for the pressure of the dry gas, then we're going to actually have to rearrange this equation. The pressure of the gas equals the total pressure minus the pressure of the water. So I'm going to plug in my numbers. I know my pressure of the gas is what I'm solving for. My total pressure was 850 torr. And my water pressure, well, you're like, okay, well, where do I get that? Well, you get that from this table right here. Specifically, we're looking at 27 degrees Celsius. We want to know what the pressure of water is. So we come down here, we find water has a pressure at 27 degrees Celsius of 26.7 mmHg or 3.57 kPa. So I need to figure out which one I'm going to use. Well, if you remember, mmHg and torr are interchangeable. So we're going to actually use this one to solve for our pressure of the water. So we'll take 850 torr minus 26.7, and we can just do a direct conversion, torr. And what we'll find is that the pressure of our gas is going to equal 823.3 torr. Okay? All right, so now I have the pressure of the gas, but that doesn't answer my question. The question asks for my volume. Well, let's see what other information I have. I know that I've got a volume. I know that STP is a temperature and a pressure. I've got another pressure here, and I've got another temperature there. So I've got two pressures, a temperature, or two temperatures actually, and one volume. Well, that sounds a lot like the combined gas law. P1 V1 over T1 equals P2 V2 over T2. So with our combined gas law, now it's just a matter of plugging everything in. So our original pressure was actually 823 torr. Okay, so this pressure right here was our total pressure, right? But they're asking for the dry. So we're just going to use the pressure of the dry. Times 50.0 milliliters divided by, actually zoom in a little bit here, divided by 300 Kelvin. Okay, and that came from our adding 273 to that 27 degrees Celsius. And that's going to equal our pressure 2, which was 760 torr. That's your STP, standard temperature and pressure. Standard pressure is 1 atmosphere, or 760 torr, or 101.3 kPa. And then we're going to multiply that by our volume 2, which is what we're looking for, divided by our temperature 2, which is that standard temperature, 273 Kelvin. And then here I like to cross multiply. Okay, and what I'm going to find is that I get an answer of 1123395 equals 228,000 for my volume 2, or times my volume 2. Divide both sides by this. And we'll find that our volume 2 is going to equal 49.3 milliliters. So that would be our answer. Okay, so if you notice, we took all those different things that we've learned about gas laws and we've actually applied them in that final problem there. Okay, so that would be everything that you need to know about your gas laws. Now let's talk about one more thing, or in terms of math. So now let's talk about one more thing, and that is effusion and diffusion. Okay, so what is the difference between the two? Well, diffusion is basically just a mixing of gases. You see diffusion when you take something like a can of Lysol or some kind of spray, and you spray it into the room, and you actually will smell it later, right, in another part of the room. So that's actually going to be those gases actually mixing in the air. Effusion, on the other hand, is the passage through a tiny hole or a tiny orifice in an evacuated chamber. So what do I mean by that? Well, what I mean is that if I take something like a balloon and I release, blow it up, and then have you ever opened up the end of the balloon and stretched it out to where it makes that really high-pitched noise? That's effusion occurring. And so it's the passage of air through a tiny orifice or hole into an evacuated chamber. So essentially into a chamber with a vacuum. Now, we do tend to think of effusion in terms of any time you're passing gas through a tiny orifice, tiny hole. And a lot of times you do end up having that little squeaky noise that occurs as a part of it. Now for this, there is a math equation that goes with it. However, you don't have to calculate that. What you do need to know is the relationship. And the relationship is basically an inverse relationship. And essentially what that means is that if I've got molecular weight The heavier an object is, the slower it's going to move, the slower the rate of effusion and diffusion. The lighter an object is or particle is, the quicker the rate of diffusion and effusion will be. Right? And so you could actually, in general, do a little test and take a couple different cans of spray, just do a little quick spritz and see if one of them actually has a slower rate of diffusion. And then that could tell you if, in general, those molecules or particles are actually going to be heavier or lighter. If you kind of point them in the same corner, do a quick, in two different corners, do a quick spritz, stand in the middle of the room and see which actually comes to you the quickest. That would be you being able to test which has a lower molecular weight, because the faster they move is based off of their molecular weight. Okay, so you do need to know that that relationship. It can be calculated the same way. Lighter gases effuse and diffuse faster. So in terms of chemistry, this is something that we would do. If we took two gases, for example, ammonia and hydrochloric acid, and we put them onto a cotton ball, and they started to evaporate inside of the tube, what you would find is that ammonia would actually start to react over here with our hydrochloric acid. Now, it's reacting over here instead of directly in the middle. Why? Well, it's happening because ammonia has a lower molecular weight. Ammonia's molecular weight is about 17.03, whereas hydrochloric acid's up there at 36, right? So we do have a large difference in our mass, and that's why we see our ammonia reacting further to the right, closer to the hydrochloric acid side of that tube. Okay? Now, all of this time we've been talking about ideal gases. I did want to mention one thing. Real gases. Real gases basically explain what happens in the real world. No gas is going to be perfect in terms of how it acts. No gas is going to follow our ideal gas law. A real gas is going to exhibit the closest to the ideal behavior if we're talking about it at low pressure and high temperature. So actually in summertime, we do see ideal or gases, real gases, acting closer to the ideal gas laws because we do have lower pressures and higher temperatures during the summer. Now, why does this occur? Why in the real world do we not see gases acting ideally? Well, it has to do with two different things. First off, if we're talking about a substance at a high temperature, there's going to be less interaction between those particles. Why? Because we know that high temperature means high average kinetic energy. And so what that means is those particles are actually moving too fast to actually interact with one another. And so at high concentrations, we can actually see a greater attractive force. But when we're talking about high temperatures, we don't see much attraction that occurs between those gases. As we increase our amount of particles that are there, they start to actually interact with each other, right? Because there's less room for them to move around, so there's going to be a lot more interaction that occurs. And so because of that, we can actually cause those attractive forces to increase. And what this does is it causes because they're now attracted to each other, when they're flying by each other, they're not going to be moving at the same rate. And so the pressure inside of the container is actually going to decrease. It's going to be because as they move across, instead of getting that full force directly into the wall of the container, instead what they're doing is they're coming full force and then they catch a little bit of pull from this particle here. And so that particle here is going to slow them down a little bit. And so when they slam into the wall of the container, which remember is how you get pressure, it's not as much as what we would expect. Another thing is that at high pressure, remember high pressure tends to happen when we've got a small volume. The volume of that particle actually becomes significant, right? So because we've got so little space for them to be, we recognize that that actually has volume and that gas is, even though we know that gas is spread to fill the container, the volume available is significantly less than the volume of the container. And essentially, your attractive forces are greater for large complex molecules and polar molecules. Why? Because they're attracted to one another. Okay. So that's just kind of a quick rundown of why gases don't act how they normally should or how we would predict they would. And so when we're doing a lot of these calculations, we're just making the assumption that that these gases are going to be behaving ideally. Because sometimes there's a lot, just not a way to actually predict their exact thing that's going to go on. All right. So that is all that we have for our gas law notes. If you do have any questions, please don't hesitate to reach out. But otherwise, y'all have a great rest of the day. Bye, y'all.